All right, welcome. Today, we're diving into one of the most incredible stories in technology. We're going to go from a simple grain of sand all the way to the absolute hearts of every single electronic device you own. We're going to figure out the secret of how we taught a basic, everyday element how to think. So, let's get into it.
It really all comes down to this one question. The rock we're talking about is silicon. It's literally the second most common element on Earth. It's everywhere. And by itself, it's not all that special. But with some unbelievably clever engineering at the microscopic level, we turned it into the foundation of everything. Your phone, your computer, everything. So how on earth did we pull that off?
So our story has to start with pure silicon, or what scientists call intrinsic silicon. I want you to picture a perfect, beautiful crystal, where every single atom is locked into place in this perfect grid. It's a total blank slate, full of potential, but not really useful, just yet.
And this is what silicon is at its core. It's a semiconductor. So what does that actually mean? Well, it's not a great conductor, like copper, where electricity just flows right through. And it's not a great insulator, like glass, that stops electricity cold. It's stuck right in the middle. In its pure form, its electrons are locked up really tight in these chemical bonds. They can't just get up and move, which means it can't really carry an electric current. But see, it's not a perfect insulator. Just a little bit of heat, we're talking just regular room temperature, is enough to give a few electrons the kick they need to break free from their bonds. Now, when an electron leaves, it leaves behind an empty spot. And we call this empty spot a hole. It's kind of weird, but this hole actually acts just like a positive charge. So now we've got these two things that can move around, negative electrons and positive holes. But in pure silicon, there's just not very many of them, not nearly enough to do anything interesting. Okay, this is where the real magic happens. It's a process called doping, and it is the fundamental hack that turns silicon from this kind of boring crystal into the engine of our digital world. What we do is we intentionally and very carefully add just a few tiny impurities into that perfect silicon crystal. And this doping process gives us two totally different flavors of silicon. On one hand, if we add an element like phosphorus, which has one extra electron in its outer shell, we get what's called N-type silicon. That extra electron has nowhere to bond, so it's just free to move around. This gives us a ton of free electrons. On the other hand, if we use an element like boron, which is missing an electron, it creates one of those holes we talked about. This gives us P-type silicon, which has an excess of these positive holes. Okay, so now we've got our two key players, one type of silicon swimming with extra electrons and another that's full of extra holes. But before we smash them together, we need to quickly understand the two ways these charges actually move around inside the crystal. So there are two main ways this happens. First, you've got drift. This is pretty straightforward. If you apply an electric field, think of it like pointing a fire hose at the charges. They all get pushed in an orderly direction. That's a current. The second way is diffusion. This is more random. You know how if you put a drop of ink in a glass of water, it just naturally spreads out? It moves from where it's crowded to where it's not. Well, electrons and holes do the exact same thing. All right, this is it. This is the moment we've been building up to. We take a piece of our N-type silicon with all those extra electrons, and we stick it right up against a piece of P-type silicon with all of its extra holes. This meeting place, this interface, is called the PN junction. And what happens next, all by itself, is the foundation for pretty much all modern electronics. The second they touch, diffusion just teaks over. Those crowded electrons on the N side see all that empty space on the P side and they just rush across. And the holes do the same thing, moving from the P side to the N side. But here's the catch. As they move, they leave behind their parent atoms, which now have a charge. This creates a zone right at the junction that has no free carriers at all. It's been depleted. And this depletion region creates its own electric field that pushes back, eventually stopping the diffusion process. It creates its own barrier. So what we have here is this incredible self-forming invisible barrier. It's a wall that just appears out of nowhere and sets its own rules for how electricity is allowed to move. And now, we're going to learn how to control those rules. Because that's the absolute key. We can control this barrier. By applying an outside voltage to our PN junction, a process we call biasing, we can either shrink that barrier down to nothing, or we can build it up even bigger. We can effectively turn it into a one-way gate for electricity. Here's how that works. If we apply what's called a forward bias, hooking the positive end of a battery to the P side and the negative to the N side, we're basically pushing the electrons and holes toward each other. This crushes the depletion region, lowers that barrier, and boom, you've got a superhighway for current to flow. But if you do the opposite, a reverse bias, you're pulling the charges away from the junction. This makes that depletion region even wider, raises the barrier, and creates a nearly perfect roadblock. No current gets through.
And I mean, just look at the difference here. It's not even close. With forward bias, current is flowing like crazy. With reverse bias, it's practically zero. We're not talking about a little less current. It can be millions of times less. We have effectively created a perfect electrical switch, on or off. So what does this all mean? It means by just doping some silicon in two different ways and sticking them together, we've built a one-way street for electricity. Current can flow one way, but it is completely blocked from going the other way. And why is that so important? Well, this simple one-way gate, that's a diode. And this exact same principle is the absolute core of the transistor. And transistors, they are the tiny, microscopic switches, billions and billions of them, that are crammed onto every microchip, doing all the math and logic that powers our entire digital world. All of it, from a simple rock to a thinking machine. Every single calculation your computer makes, every pixel that lights up on your screen, every piece of data that flies across the internet, it all comes back to this beautifully simple thing that happens when two types of silicon meet. It was the first giant leap in teaching a material how to compute. And that just leaves us with one last question. What's the next material and the next kind of junction that we're going to teach how to think? Thanks for joining me for this one.